Recorded now. Okay, so we're talking about boundary layers, and I asked you to do this thought experiment. When you're close to the ground, we're hardly experiencing any wind, and actually if you were to go down really flat to the ground, we have the no slip boundary conditions for any viscous flows, and we would experience even zero velocity. So if I draw the situation, if I sketch it here on the blackboard, we have a situation which looks like that. We have the ground here, green grass, and when we're sitting, oh, sorry, I need to switch over to my video. And when we're sitting on the ground, we experience zero velocity. And if we're high above the ground, like an observation tower, we experience high velocity. And this is actually a gradual increase from zero to an elevated velocity. There's a certain distance away from the ground where the velocity will not increase anymore. Well, maybe it increases to go very, very high. But this gradual increase has a certain typical thickness. We typically denote by delta. So this is the boundary layer thickness, and that little thing here is called boundary layer. On a day like today, the boundary layer thickness of the wind going over the ground is probably, let's say, 20 meters, 30 meters, maybe 50 meters. If you have a boundary layer on a different object, for instance, on a wing, turn the laptop a little bit. We have an airfoil here, and on the surface of the airfoil, you will again have zero velocity, and farther away, you'll have a constant velocity, and there's a thin layer in which the velocity gradually increases. Let me mark this thin layer by the red color here. So in this thin layer, we have this gradual increase in velocity with a thickness delta. On a wing, this typically is a few centimeters. Actually, depends a lot on the Reynolds number itself. So we'll look into this more precisely. So very thick boundary layers, thinner boundary layers, all kinds of things. But boundary layers appear almost everywhere. So let us switch back to the slides. And let's look at the whole theory of boundary layers, because there's some history to it, which is worthwhile to explain. And we should, to this end, look at the situation in the early 20th century. So this is roughly 110 years ago, or let's say 120 years ago. So 1900, 1910. At that point in time, several things in fluid mechanics are already known, well known. For instance, what we did last week, like the Stokes solution, Stokes drag on a sphere, low Reynolds number flows. This is something which was already quite a bit understood. It was understood what the effect of viscosity is. And there was another thing that was well understood, and that was solutions for inviscid flows, so flows without viscosity. And that's actually something we'll start doing next week, right? Sort of the opposite of what we're doing today. And this theory of inviscid flows gave quite good predictions for the streamlines around the wing. Let me draw these streamlines. So people were able to draw streamlines around wings. And they used this theory of inviscid flows. They were even able to compute lift forces on wings. So they could compute how much lift you had on an airfoil. But whenever they tried to predict the drag force on a thing like an airfoil, that theory, that implicit theory, completely failed. Because this implicit theory, we'll see this maybe not next week, but in 2 weeks, this implicit theory predicts zero drag for things like an airfoil. So obviously, this cannot be true. So there was this weird situation. Streamlines looked okay, lift looked okay, drag was obviously completely wrong. And so there must have been something missing. And that missing thing was really the theory of boundary layers. So really this thin layer just above the surface of an airfoil or thicker on the surface of, let's say, the ground. And it was Ludwig Prandtl, he was a scientist in Göttingen, the University of Göttingen, at the beginning of the century, who developed the boundary layer theory, which became hugely influential, not only in fluid mechanics, also in, let's say, in applied mathematics in general. A lot of physical applications are now using Prandtl's boundary layer theory. The whole perturbation theory that is used in many different applications in physics and applied physics are based on Prandtl's theory. So what was Prandtl's idea? Prandtl said, well, obviously, we have two regions of a flow. We have an outer flow, shown here by the blue streamlines going around the airfoil, and then these blue regions, like the bulk of the flow, viscosity is unimportant. We can actually use implicit theory. And close to the surface, we need to compute something he coined the term, he called boundary layers, where viscosity is hugely important. And so he was splitting the whole flow problem in two regions. One of his contributions was also to show how to match the solutions for these two regions, right? So the outer edge of the boundary layer must comply with the inner edge of the outer implicit flow. So you get one complete unified solution. So you see this here schematically on this slide again. We have the inner solution, the boundary layer solution, where we look at viscosity, and we will have the outer solution, sometimes called the free stream, the far field. And in this free stream or far field, we have an irrotational flow, which has to be matched to the outer edge of the boundary layer. This whole irrotational flow thing, this is a separate theory, and this will be the topic of the next 2 weeks, called potential flow theory. And it's very beautiful, but it's completely different from what we do today. Today, we're only looking at the inner solution, at the thin layer on the surface of a wing, the boundary layer. Now, one very important thing we need to appreciate in this context is that the inner solution needs to satisfy the no-slip boundary condition. So what is the no-slip boundary condition? If you go back on the blackboard, no-slip means we have zero velocity at the wall itself. This is a boundary condition we must satisfy on the wall. Any viscous flow has zero velocity on the wall. Let's go back to the slides. So what does this mean in terms of the equations? We have here our basic Navier-Stokes equations again. And you see on the top line, the continuity equation, actually this will remain as it is. But on the second row, where we have a momentum equation, we have this term here, the last term, which we usually call the viscous term. This is where the viscous effects are contained. And we know, let me take this away again, we know that the viscous term is multiplied by the factor 1 over Reynolds. And so in the case of high Reynolds number flows, where inertia is dominant and viscosity is relatively small, this term obviously 1 over Reynolds becomes small, and that's why people 100 years ago, 120 years ago thought, let's just get rid of this term. And that poses some problems. So those people who cut off this term, these were the people who came up with the blue streamlines, the inviscid solution, the solution neglecting viscosity. So why is this not necessarily a good idea? It's not a completely bad idea, but it doesn't hold the whole story. Why is it not necessarily a good idea? Let's just see what is written down here. The term that we just deleted here is a so-called second order term. It's a term with a second derivative in space, right? It's a d squared u dx squared, or du dy squared, or du dz squared. So a second derivative in space. If we eliminate this term, because we think it's small and small terms can go away, it's not just that we're neglecting a small term, we're completely changing the character of the equation, because look at all the other terms. The first term, unsteady term, is a first order derivative in time. The second term, although it's a nonlinear term, it's only a first order derivative in space, right? The gradient operator is a first order derivative. And then we have the pressure term, again, a first order derivative. So by deleting this term, we make out of a second order equation, second order partial differential equation in space, we make a first order partial differential equation. If we reduce the order of a differential equation, one of the practical effects is that we have, instead of two integration constants, we have only one integration constant. And what are the integration constants good for? Maybe you can remember back, I think 2 or 3 weeks ago, when we derived the solution for Poiseuille flow between two flat plates. We also had two integration constants, and we determined the integration constants by satisfying the boundary condition at the lower wall and the boundary condition at the upper wall. Right? So two integration constants, two boundary conditions. If we delete the higher order term and go to a first order equation, we only have one boundary condition left that we can satisfy. So what does that mean? Throwing away the high order term leads to a solution that has only one integration constant, and we can only satisfy one boundary condition. And the boundary condition we can satisfy is the outer boundary condition. So for instance, if the airplane is flying with a velocity u or sees a velocity u coming toward it, we know that somewhere far away from the airplane, we have a velocity u up here. I hope you can see that. Huh? So we have a boundary condition far away for y to infinity. And the second boundary condition would be the one that u must be 0 at the wall. And that we cannot satisfy anymore if we throw away this term. And this is why it's not a good idea to completely throw away, neglect the viscous term, even though Reynolds number might be high. Because once we throw it away, we cannot do no slip at the wall anymore. And that's something that Prandtl understood. By the way, these equations, they have a name. Equations where the highest order term has a small coefficient in front of it are called singular differential equations. Up here, singular differential equations, because you have a singularity in the relevant term, in the highest order term. So Prandtl realized that we need to be careful about the second derivative in space, we need to maintain it somehow. And here's what he did. And this is now really magic. This is really intuition, genius of Prandtl, that he came up with this equation, which are nowadays known as the boundary layer equations. If you look at them on the bottom, they look quite similar to Navier-Stokes equations, but he threw out quite a few terms. And why he did it, I don't really know. He just did it. And only with hindsight, by solving it retrospectively, he was able to show that this was actually a good idea. But there's no rigorous mathematical way why he could write it that way. This was really a stroke of luck, genius, take it how you like. So let's look at these terms here. Hope you can see my mouse pointer. On the left-hand side, we recognize here the nonlinear term of the Navier-Stokes equation. The unsteady term was kicked out because he said, we're just looking at steady solutions, that's okay. So he left the nonlinear terms. He left the pressure gradient. And in the viscous term, he left the second derivative in y direction. But the second derivative in x direction, he kicked out. So let's look at this again on the blackboard, what this means. Let me draw maybe a slightly bigger diagram here. If we assume we have a flat wall, I'm not doing an airfoil now, just a flat wall, plate if you like. And there's an airflow coming from the left with velocity u will obtain boundary values. Just like what I drew above with zero velocity at the wall. And if we call it here a y direction, and we introduce here an x-axis. What Prandtl observed was that the shape of the boundary layer changed only very little as he moved in x direction. There is some change, and we'll see this in a minute, but the change was very, very slow. So he says the second derivative in x direction is small, and he neglects it, but the change in y direction is quite rapid. It goes from 0 to a high velocity u, out here, far away from the wall. You must have capital U. That is quite rapid, especially if the boundary layer is thin, then this change is quite rapid. And that's the reasoning why he decided to maintain the derivative in y direction, but to kick out the derivative in x direction. And by that trick, he was also able to maintain the equation, a second order differential equation, especially in the y direction. So he was able also to satisfy the no-slip boundary condition at the wall. So that was Prandtl's basic main contribution to boundary layer theory. He then went on and he had a student, a PhD student called Blasius. I think that was around 1910. And he gave Blasius the job to solve these equations, find a solution for these boundary layer equations for a very special case. And the special case is, look at a flat plate, large flat plate, infinitely large or semi-infinite if you like, and consider a flow with a zero pressure gradient. And Blasius solved this problem, and that's why it's now called the Blasius boundary layer. So let's look at it. What did he do? So he looks at a boundary layer on a flat plate. This is more or less what we drew here on the blackboard. And he assumed that there's a zero pressure gradient. And we need to look at this a bit more closely. So what does it mean, zero pressure gradient? It means that outside, I'm always talking about outside of the boundary layer, the pressure is not changing in downstream direction. So the dP dx is not changing. And if dP dx is not changing in downstream direction, think of the Bernoulli equation. That also means that the flow outside, at the outer edge, the U, will not be accelerated. Out here, away from the boundary layer, we have zero viscosity. So if we have a negative pressure gradient, we would accelerate the flow. If we have a positive pressure gradient, we would decelerate. That comes out directly from Bernoulli. Let me maybe quickly write that down. Bernoulli tells us that pressure plus 1/2 rho U squared must be constant. So if the pressure is not changing, neither will the velocity change. Okay, so this is one condition. We have a zero pressure gradient, meaning that the outer velocity will always be zero. By the way, sometimes on some slides it's called UE for U at the edge, and sometimes just called capital U. I'm sorry about that, but this is the same thing. Now the next thing, and that's again a very important observation, again it's a bit of a stroke of luck or of genius, a very important observation of Blasius. He observed that these boundary layers at different locations on the flat plate, they have a very similar shape. He also observed that as the farther he went downstream, the thicker the boundary layer becomes. So if we see how quickly it goes from 0 to U here, maybe it takes that thickness, and here it's a bit larger, and here it's even larger again. So he saw that they're becoming thicker and thicker and thicker, and actually he made the observation that the thickness of the boundary layer, which he denoted again by delta, that delta is increasing like the square root of x. Again, that was an observation. It was really something he just saw. And so Blasius had the idea that he could describe the shape of the boundary layer by one single function. So he would not have a flow field like a Eulerian flow field of u of x and y. He would just say it's a shape, a certain shape function, and he would just keep on stretching it. Or, mathematically speaking, what he did, let's go back to the slide, he introduced a new coordinate, a new wall normal coordinate, coordinate eta. and he normalized this coordinate eta, or he wrote it as y divided by the thickness. Okay, so he had a y coordinate which scales with the increasing boundary layer thickness. And then he made the ansatz, and that's the one you see also on the same line. He made an ansatz that the stream function of the solution is equal to u, that's the outer flow velocity, times the thickness times f of eta. And f is now this shape function, the unknown shape function, which describes the shape of this Blasius boundary. And for the thickness, he used the following ansatz you see on the bottom line. And let me do this again on the blackboard because I think it's important you understand that. Start on top again. For the boundary layer thickness, I already told you he made the observation that the thickness is increasing with the square root of x. He also found the thickness is not just increasing with the square root of x, it's also increasing with the viscosity nu, with length x, and it's getting thinner with the square root of u. That was, again, a bit of genius that he just wrote it down that way. So it was really an ansatz by Blasius, or maybe Prandtl. There's actually something we can do with this boundary layer thickness. We can that as well. We can expand here, we do it separately, by x. So we put an x square here, and we put an x in the denominator as well. And then we pull out the x square out of the square root, and we get x times square root of nu divided by x times u. Okay? So maybe you recognize what we have here. We have a length times a velocity, and on the other side we have a viscosity. This is like a Reynolds number, or the inverse of a Reynolds number. If we define Reynolds x, put the subscript x to indicate that it's Reynolds number with x. If we define Ray x as x times u divided by nu, then we can just write this like that. Okay. Write this a bit nicer so you don't get confused. With a new Reynolds number defined as x times u divided by nu. This is the new Reynolds number that we're going to use for this Blasius boundary layer. It's a Reynolds number that increases the farther we go down. Right? It's a Reynolds number that increases as we're going down the plate. Huh? It starts with Reynolds small and goes to Reynolds higher and higher and higher. It has something to do with the thickness of the boundary layer or the downstream distance. And we can describe the thickness of the boundary layer, thickness delta, can be written as x divided by square root of this Reynolds number. Just a non-dimensional way of writing. Okay, let me go back to the slides. Okay, so Blasius introduced this description of the thickness. He introduced a normalized wall normal coordinate to get some kind of a self-similar solution. And he made this ansatz here that psi, the stream function psi, is equal to u times the thickness delta times the shape function f of it. And what did he do? Well, now he has an ansatz, and we know that from a stream function psi, if we take the derivative with respect to y, d psi dy gives us velocity u. And if we take the derivative with respect to x, or minus d psi dx, we get velocity v. Okay. So from this ansatz, we can write down expressions for u and v. I can actually do that. It's down here. Blackboard is a bit small. I'm sorry about that. So for the ansatz, psi equals u times delta of x times f of eta, eta being the new coordinate, the new normalized coordinate. We can also write down an expression for u. The velocity u is defined as d psi dy. So if we take the y derivative of this expression, what do we get? We get u times, this is just a factor, it's not changing in y, so it's u times delta times f. Now, the derivative of f with respect to y, again, we have to use the chain rule, so it's f prime, the derivative with respect to its argument, and then according to chain rule, it's a d eta dy. And if you check out what d eta dy is, you can do this at home, you will see that d eta dy is exactly 1 over delta. Okay? You can see that. So the red chalk here, we have a 1 over delta here, and we have a delta there. So u is exactly equal to u times f prime. Okay? And you can do the same for v, where v is minus d psi dy. And I'm not going to do this, but you can also find an expression for v. So based on his ansatz, he was now able to write down expressions for u and for v in function of the unknown f. And he would go back to his boundary layer equation So I'm going back one slide now, 2 slides. And he plugged in wherever he had a U, he would plug in this U times F prime. Here also the U times F prime. For V, he will plug in whatever V is. The pressure gradient actually by definition is 0 because he's looking at the 0 pressure gradient problem. And you can also compute what du dy squared is. You can go through that and you can actually look this up in books or do it by yourself. It's not that difficult actually. What you will end up with is a differential equation for f, for the unknown f, which is really just the shape function. And you can solve it. It's at the time of Blasius, it was a complicated differential equation, but it was an ordinary differential equation. So he found approximative solutions. Nowadays, you can just use MATLAB too. So you can find solutions for f, which solve the boundary layer equation, and you can look at the results. And let's look at the result on the left-hand side first. This is the streamwise velocity u. So essentially this is u times f prime, plotted with respect to this coordinate eta, and here plotted with respect to u divided by capital U. So it goes from 0 to 1. So it's not like we plotted it before, it's like flipped, like by 90 degrees, if you like. So at the wall is here, this is the wall here on the left. There's 0 velocity, it's increasing and reaching the outer velocity 1 here. And you get a result also for the wall normal velocity. And you see that the wall normal velocity is not 0 in a Blasius boundary. It is small, it's actually a lot smaller. And you see this due to this factor here, you will actually find that the wall normal velocity, let me look this up to be correct. The wall normal velocity is smaller than the streamwise velocity by a factor of square root of Reynolds. It's really a lot smaller. So why is the velocity not 0? And to this end, you need to look at this picture again. The boundary layer is getting thicker and thicker and thicker. So especially fluid particles on these outer edges of the streamline, you need to have a slight shift of velocities also in the vertical direction. Otherwise, you could not get the boundary layers thicker. So you need some rearrangement also in the wall normal direction. This is why you have a non-zero wall normal velocity in the Blasius boundary. Let me just finish up before we take a break with some more results on the Blasius boundary layer. First of all, there's something which may or may not confuse you, or at least it confused me when I saw it first. I introduced this whole story with this boundary layer thickness delta, right? We had this delta, and I told you it was a bit of genius of Blasius and of Prandtl to find this expression for delta. Now, it was a good idea, but what they did not know beforehand is that, yes, the thickness scales with this factor, but it's not exactly like this factor. It's not the same. So the real boundary layer thickness is not just this delta, it's a multiple of this delta. And we see this on the slide here. On the left, you see the boundary layer and the streamwise boundary layer, and you see here the coordinate, and you see actually that the thickness of the boundary layer is more something like 5 or 6 times this delta. The delta itself is where eta is 1. Okay, so in that sense, the scaling is good, but the factor was wrong, And he needed, for practical reasons, if you want to describe how thick the boundary layer really is, you need to come up with some other measures. And there's a whole zoo of different boundary layer thickness measures. And maybe the first one is the most obvious one, is this 99% boundary layer thickness. This is defined as the distance from the wall where the velocity, the streamline's velocity, reaches 99% of the free stream velocity. So if I go back one slide, this would be probably somewhere around here, where we have reached 99% of the edge velocity. I think this is intuitively what most of us would think of as a boundary layer thickness. And we see that this delta 99, as it is called, is somewhere around, I think for the Blasius boundary layer, is about 5.5 times the original delta of Blasius. But we have other measures. There's also another one which looks mathematically a bit complex. It's called the displacement thickness. It's actually quite useful because when you look at this diagram here, when you look at this diagram here, you see that the outer streamlines, because the boundary layer has a certain thickness, and in terms of mass conservation, let's look at Blackboard here again. If upstream from the wall, upstream here, we have a uniform velocity profile. All the velocities are the same before they start hitting the tip of our flat plate. And now in terms of mass conservation, at each location, different color, we're missing that little bit of volume, or here we're missing even more. That little bit of volume is missing, or here even more. That little bit of volume is missing. And this tells us how much, my blue chalk here, how much the outer streamline, the blue streamline, has to be displaced upward, right? It's displaced to compensate for this amount of fluid that we're not transporting here. And the amount of displacement due to the boundary layer itself, that's called the displacement thickness. And that is actually given by this integral here. This integral here is giving a displacement thickness. It tells you how much the streamlines are displaced. It's also shown in this diagram down. There's a third commonly used measure, different formula, and it's called the momentum thickness. It's describing how much momentum is lost due to the boundary layer. This talks mainly about the viscosity or the viscous effect, the viscous losses due to the boundary, but we'll not go too much into that. So for the Blasius boundary layer, these thicknesses, they have specific expressions. So we see here, delta 99 is 4.93 times the original delta, or you can also express this in a non-dimensional way with the square root of Reynolds X. This is the expression for the displacement thickness, also given as 1.72 times the original delta, and here is the momentum thickness. Now, what did I say about this wall shear stress? Well, at the wall itself, we have zero velocity. We do have a certain gradient, so we will have, use yellow for that, we'll experience a shear stress tau at the wall, right? because we have these viscous forces. The thinner the boundary layer is, the higher these forces are, because the gradient here is steeper, here it's more shallow, and here it's even more shallow. So actually the wall shear stress decreases as the boundary layer becomes thicker, and there's an expression, explicit expression for that on this slide, telling us that the wall shear stress tau is 0.332 times rho u squared divided by the square root of this Reynolds X. So it's a nice, neat expression for lossless boundary. And of course, when we integrate all shear stresses on the wall, so we're essentially summing up all these contributions from the shear stresses for a whole plate of a whole length L. So we're integrating over the length L of a plate, we get a complete drag force. And we know, we have learned that in Stokes flow, but I also learned it in Buckingham pi, that we can express the drag also by drag coefficient, which is given as drag force divided by 1/2 rho u square L, in that case, L being the length of the plate. And that can be expressed by 1.33 over square root of Reynolds L. Reynolds L now, mind you, this is just like Reynolds X. Reynolds L is when we have an L here in the denominator, in the numerator of the. So this expression down here, it's just like the same story that we had last week for the Stokes drag. Right there we had a drag coefficient which was 24 divided by Reynolds. Now we have a drag coefficient which is 1.33 over the square root of Reynolds. But again, it has been shown that the drag coefficient can be expressed, the non-dimensional drag coefficient can be expressed in terms of a Reynolds number and nothing else. Results like the one on the bottom are usually summarized in diagrams like that. And you see that result in this diagram on the bottom left is this curve here, this black curve denoted by laminar. So the drag coefficient decreases as the Reynolds number of the plate, L is the length of the plate, increases. Okay. What about the other curves? Well, the lossless boundary layer is a laminar boundary layer. Everything is laminar, no turbulence. If the boundary layer becomes turbulent, and we'll look at this in lecture 9, the shear stresses will increase and the drag will increase. This is why if you go to turbulent cases, we have higher drag coefficients. Drag coefficients are elevated. There's also a transitional regime when you're in between laminar and turbulent. And these lines here with the different numbers, these are actually roughness heights. So if you have a rough plate with asperities, it will create more and more turbulence, and obviously intuitively clear, the drag coefficient will increase. So this is a very typical diagram that we have for the drag of a plate. But the bottom left curve here is just the lossless boundary layer as we have derived. Okay, so it's time to take a break now. Let's meet again at 2:20, and then we'll continue. Welcome back to the lecture. We will continue with the slides, and you have seen before in the previous hour what the Blasius boundary layer looks like. The Blasius boundary layer is maybe the most simple, maybe the prototypical boundary layer per se. It's a boundary layer over a flat plate for zero pressure gradient. And in that case, in the context of boundary layers, zero pressure gradient mainly means that the outer flow velocity is not changing as we go downstream in x direction, right? We have the same outer velocity u, a constant velocity u, as we go in downstream direction. That is, for instance, the case over a flat plate. But we know that not everything that is subject to an airflow is a flat plate, and that, for instance, an airfoil is anything but flat. And that a lot of the function of an airfoil has to do with the shape, the camber of the airfoil, for instance, but also other objects, for instance, like a ball, like a tennis ball or a football. They're certainly not flat plates, and the airflow, and I'm talking about the outer flow, not the boundary layer itself, the outer flow will experience acceleration and deceleration as it goes around the object. So there was a need to extend the basic Blasius boundary layer theory from zero pressure gradient boundary layers to non-zero pressure gradient boundary layers. And this is work which was due to Faulkner and Scan, so these are two names, and that's why it's called the Faulkner-Scan boundary layer. Or actually, as we will see in a minute, the family of Faulkner-Scan boundary layers. So, here in the slide, yes. So what are Faulkner-Scan boundary layers? These are boundary layers for non-zero pressure gradient. And as I tried to show before, the pressure gradient immediately translates into a velocity in the outer field. And Faulkner-Scan described the outer velocity, here again denoted by UE. They described this by a polynomial. So for the case of n, the exponent n being 0, UE is a constant. So for n0, we have the situation where we have a Blasius boundary layer. So Blasius is contained within the theory of Faulkner-Scan for the special case of n0 for constant UE. If n is a positive number, x to something positive increases in x direction. So that means the flow is accelerated. So we have an accelerated flow. Or in terms of pressure gradient, it means that the pressure gradient in the outer field is negative, right? Again, with Blasius, if we have a negative, not Blasius, with Bernoulli, if we have a negative pressure gradient, we're accelerating the flow. You will see in a minute why this is called a favorable pressure gradient. The opposite, n smaller than 0, n negative, means that the velocity decreases in x direction. We have a decelerated flow in the outer flow field, or an adverse pressure gradient, or an increasing pressure gradient, positive gradient, increasing pressure. On the third line here, you see how a pressure gradient and outer flow velocity relate to each other. We have minus dp dx equals u du dx. If you integrate that, this ends up being exactly like the Bernoulli equation. Or take Bernoulli, pressure, put this on the right-hand side, pressure plus 1/2 u squared, 1/2 rho u squared is equal to, there's actually a row missing here, just is exactly constant. So if you take the derivative with respect to x of the Bernoulli equation, you get exactly this expression. Yeah. So here you see how the pressure gradient is related to this parameter n. But for now, it's sufficient if we just remember n positive is accelerated flow, decaying pressure gradient, or decaying pressure, negative pressure gradient. For n negative, we have a decelerated flow and a positive pressure gradient, or also called adverse. If we look at the situation we have on the surface of a curved object, so for instance, the upper side of a wing, or the upper side of a ball flying through the air, we see all configurations down here. So the object on the bottom right is subject to an airflow coming on from the left with u infinity, and it should be clear that when the flow goes up the hill or up on the upstream side of the object, just due to mass conservation, it has to be accelerated first. It has to flow faster. Otherwise, mass conservation could not be satisfied. So we have an accelerated flow on the upstream side of objects. And on the downstream side of the objects, we have a decelerated flow. And exactly on one point, and namely on the top point, on the thickest point of this ball, or on the thickest point of an airfoil, we have one single point where we have zero pressure gradient. It's just switching between accelerated and decelerated flow. And that's exactly with zero pressure gradient, we have a Blasius boundary. So in this little diagram, you see the Blasius boundary layer, you see a boundary layer for an accelerated flow, and you see a boundary layer, for a decelerated flow. So what the Faulkners can do, they took this ansatz here, derived what it means for the pressure gradient. So essentially, you just have this term here. You put it in the Blasius and the Prandtl equation, the Prandtl boundary layer equation. You replace the PDX by this little expression, and then you solve it again. Again, this is a bit of a tedious thing to do, and we'll not walk through that. I'm just going to show you the solutions. You have them here on the bottom left. These are boundary layer solutions, again shown in this self-similar shape function f prime, just as Blasius did it. It's now shown for the Faulkner-Scan boundary layers, and again with a normalized coordinate. And you see here in the middle there is a curve for n0. So this curve here, this is exactly our Blasius boundary layer, absolutely identical. Blasius, and for accelerated flows, we get these curves up here. So what usually people are calling this is, they say the belly of the velocity profile increases. Let me maybe draw this on the blackboard here just to make this. Okay, I think I quickly dropped out. Okay. For back, I was just talking about the different boundary layer shapes. And I was trying to tell you to draw on the blackboard different shapes, how the shape is changing. So I'm drawing the wall first, which is now not necessarily a flat wall anymore, but just one part of the wall with the y coordinate, and this here being the prototypical Blasius boundary layer. Maybe mark it in blue. So this is Blasius, or the boundary layer for dp dx equals 0. if we do have an accelerated boundary layer, an accelerated outer flow, so the outer flow is increasing in downstream direction, the boundary layer tends to have a bigger belly. So this is an accelerated outer flow, also called a favorable boundary layer. In the opposite case, and we have seen on the slide, on the previous slide, this is the accelerators on the upstream side of an object. On the downstream side, we're decelerating the flow. The boundary layer is doing something quite special. It gets an inflection point. And that inflection point becomes more and more extreme. So these here are boundary layers, Faulkner scan boundary layers, for increasing pressures or positive pressure gradients. You can think of that as the flow is decelerating. The flow in the boundary layer is decelerating. And actually, the situation from a bigger belly to Blasius to a decelerated flow with an inflection point here in the velocity profile becomes more and more extreme. And you can probably imagine that if you look at the gradient here at the wall, there's one point where you exactly have a zero velocity gradient at the wall. In this boundary layer here, that one particular case, we have du, dy at the wall exactly zero. It's a very special situation. You have zero velocity gradient at the wall. That means for this boundary layer, you have zero stress, zero wall shear stress at the wall. And this is happening on the downstream edge, on the downstream side of an object like an airfoil or a wing. What is happening if we go beyond this point? The boundary layer is doing this. What happens if we go beyond this point? Well, there is, let me yet use another color. That will be the point when the flow close to the wall starts going in the opposite direction. Huh? So far away, it looks like a normal boundary layer, but very close to the wall, we have reverse flow. Flow is going backward. So something has happened, something fundamentally different, something fundamental has happened to the boundary layer. And this is a phenomenon which is known as separation, flow separation, or boundary layer separation. You see it here again, Blasius, and here we're going to nearly a zero gradient at the wall. And if we go beyond that point, that's exactly what's shown here on the bottom left, we even can get reverse flow. The point where this all starts is called the separation point, often denoted by a capital S. The separation point is exactly where we have this one boundary layer where the velocity gradient is zero. Zero stress condition here. Upstream of this S, we have a normal condition. We have shear stress creating a drag in a positive direction. Beyond that separation point, we have reverse flow going the opposite direction, and shear stresses point upstream. And flow separation is a phenomenon that is well known. For instance, here in this diffuser, you get flow separation. And we'll see, I think, in 3 or 4 weeks when we talk about aerodynamics, that flow separation is a very well-known phenomenon on airfoils, and it creates a stall condition in airplanes. So when airplanes are stalling, essentially falling out of the air because they lose most of their lift and drag increase dramatically, this is the situation of flow separation. Does not necessarily have anything to do with turbulence. So per se, flow separation does not have to be turbulent. Very often this gets confused. Flow separation creates stall. Turbulence does not create stall. Very often separated flows are turbulent, but in the first place, separation is the bad thing. Remember that, but we'll come back to it. Okay, so we have flow separation, and this is like a special case where the Faulkner-Scan boundary layer goes beyond a certain critical point, and we get this reverse flow situation. Good, so this is the family of Faulkner-Scan boundary layers. It allows us to describe, at least in 2 dimensions, most of the airfoil of the boundary layers on the surface of, let's say, a blunt object of an airfoil. Let's take a look at yet another boundary layer solution. It's a bit of a special thing, but I think it's cool also because it has an exact solution. It's one of the few cases where we don't need to use Prandtl's approximations, where we can actually find exact solutions to the Navier-Stokes equation. And that is the so-called asymptotic suction boundary layer. And I will show you that this is not just an esoteric academic case, this is really something that is being used by the aerospace industry. I'll show you some pictures of that later on. So what's the idea behind the asymptotic suction boundary layer? Let me just take my notes and get out of order with that. Yes. So I'll go back to the Blackboard view. Yeah. Okay. So let's imagine, actually we can get rid of, let's get rid of that one. Just imagine we have a wall, flat wall for now. We have an airflow over this flat wall. In blue again. With an outer velocity capital U again. Now, there's one thing we do differently. We make little holes in this wall, or in a mathematical sense, we make this wall porous. Porous in the sense that we can suck a little bit of air through the wall. So in practice, we'll see a picture of a test airplane by Airbus. They actually drill little holes in the surface of the wing, and they suck out some air. And you make sure you put a pump there such that air is eliminated, is sucked out from the boundary layer with a constant velocity VW. In addition, we assume that we have a steady situation, and we assume that we have a situation where du dx and dp dx are 0. So it's a bit of a translational invariant. We just say nothing is changing in the next direction. finally, we're gonna assume, or actually you can even show that, but we're not gonna do it, that if this again is the x direction, this is the y direction, that there is a flow field everywhere such that, see this, yes. So V is equal to minus VW, right? And that's true everywhere. So we just essentially have a translation, a slow translation of fluid into the wall. But because we have a flow from left to right, we'll develop some kind of boundary layer. And because nothing is changing in x direction, we already know that this boundary layer is only a function of y. Now let's see if we can find an exact solution for this boundary. Let me write down the Navier-Stokes equation or the momentum balance in x direction for this flow. I'll write like that: u du dx plus v du dy equals minus dp dx plus nu. I use here nu, that's why I did not write the rho here. I divide everything by rho times the second derivative of u in x direction plus the second derivative of u in y direction. Now there's a lot we can throw out. We can throw out the first term because we're looking at the steady flow situation. We can throw out this term because we have a du dx, and we assume this assumption that nothing is changing in x direction. This term here, v du dy, we cannot throw out because v is non-zero, and du dy, well, it will also be non-zero. There will be a non-zero pressure gradient. So this term remains. dp dx, again, we impose that there's zero pressure gradient. And out of the viscous term, the du dx goes away because we assume nothing is changing, and that remains. So the equation that we end up with is the following. V, we already know it's minus VW, so it's minus VW times u dy, and because u is only a function of y anyway, I just simply write u prime as the first derivative. And on the right-hand side, we only have a nu for the viscosity, and the second derivative, that's u double prime. Or we can also write this like that, u double prime, I bring this to the same side, plus v w over nu, u prime equals 0, subject to the boundary condition, u must be equal to 0 at the wall, right? We have a no-slip boundary condition, u direction. The suction only works in the y direction, and we need to have a velocity u, capital U, at y to infinity, or let's say far away from the wall. This is now a relatively simple ordinary differential equation. It's one with constant coefficients. This is a constant here, and this is just u double prime u prime. I'm sure all of you have learned how to solve this. So I'm just going to write down the solution, and it will be a solution in terms of exponential functions. And the solution is, now actually I need to go down even more. The solution simply is the following. U of y is equal to capital U times 1 minus e to the minus y times VW over nu. Parenthesis closed. I hope you can read this. And this is minus y times this is VW over nu, this factor here. So what is this? This is just an exponentially decaying function, and it's decaying with nu over VW as a length. So if we go back here to our solution up here, the shape of the boundary layer is essentially this here is like a decaying exponential. And the decay rate of this exponential is exactly this nu over VW. Yeah? Different color. The slope of the exponential decay is given by nu over VW. What does this mean? The more viscous it is, the thicker the boundary layer becomes, and the more we're sucking, the higher VW, the thinner the boundary layer becomes. This is a very special boundary layer. Well, first of all, it has a really simple solution, just an exponential. And second, it's one of these boundary layers that is not getting thicker with x. The classical Blasis boundary layer is always thickening up more and more and more. Because we're continuously sucking out fluid through the wall, we can maintain a constant thickness. In addition, and that's something we will talk about in lecture number 9, this is a boundary layer which happens to be very, very stable. It's very keen to remain laminar. Blasis boundary layers become turbulent at one point. Asymptotic suction boundary layers are very stable boundary layers. And that's something the airplane industry is using to reduce drag, because a lot of the drag on an airfoil is due to turbulent drag, to turbulent boundary layers. So people want to maintain boundary layers laminar as long as possible. And you see here on this picture, bottom right, the tail fin, I think it's of an A320, and they drilled, especially here on the leading edge, little holes where they evacuate the air. You see here again the shape. This is the way the shape of the asymptotic suction boundary layer, and the squares or the diamonds here are the Blasius, and the open symbols I think are the asymptotic suction, and the yeah, exactly. The symbols are the Blasius boundary. So they did tests, obviously, here in the wind tunnel. That's a picture of a wind tunnel. They also did in-flight tests, actually, with an A320 test plane, and they could actually show that the fuel consumption is reduced by approximately 1 to 2%, which may not seem like a lot to you, but once you get into the field of airplane industry, of optimizing these machines, or if you get into optimizing gas turbines, all kind of flow machines, you will see that reducing drags, reducing fuel consumption by 1% is actually huge. It's really, really enormous. And there was big hope that this could be used in practice. Now, if you look at the year down here, this is something that was done in 2000. I was actually still a PhD student when I heard the first talk about these asymptotic suction boundary layers. I don't think this really went anywhere, or I'm absolutely sure there's no airplanes today that are being sold with these holes in the wing, not for safety reasons, but the main reason is that there's a maintenance problem with these holes. They do what they're supposed to in terms of physics, but at the same time, if you have them in operations, these holes, they will clog, right? So you will need someone who's continuously cleaning out these holes. Plus, we must not forget that in order to suck out the air out of the boundary layer, you need a little motor, a little pump to actually drain this air. So it's not as simple as it seems. At the same time, it's always nice that we see that a relatively simple solution we can discuss on a blackboard actually finds its way into technical application here at an Airbus A320. Good. So we have about 5-6 minutes left, and I would like to finish up with a little excursion into three-dimensional boundary layers. So everything that we have done so far are two-dimensional boundary layers, right? We started off with a Blasius boundary layer, flat plate, zero pressure gradient. We saw its thickening. We extended to Faulkner scan, where we have accelerated and decelerated flows. We learned about flow separation. We looked at just last minute at the asymptotic suction boundary layers, but everything happened in a plane, in a two-dimensional plane. Now, this is not always the case, or actually it's very often not the case in reality. In reality, very often we have three-dimensional boundary layers. What happens is that the velocity profile is rotating as we go away from the wall. This is indicated by this diagram down here. Now, this might be a little bit confusing to you at this point, but there's a relatively simple case where I'm sure all of you will understand what's going on. So just imagine you're sitting on a sailboat and you're going in a certain direction, right? You're going back to let's say to where you started. So you have a certain direction, and there's wind coming. Let's say your wind is coming from right behind you. So if you imagine you were climbing up on the mast to the top of the mast, you will probably mostly feel the wind coming from left behind you, right? Maybe you will be slightly deflected because your boat is going forward, but you add up these two vectors and you get a resulting vector which is somehow pointing roughly in the direction of the wind speed. What is happening if you go very close to the surface of the water? We know from the basic concept of boundary layers of no slip that there will be zero wind on the surface of the water, right? On the surface of the water, wind speed will be zero. However, since your boat is moving over the water, you will experience on the surface of the water a wind coming toward you exactly in the direction of motion of your boat. Okay. So on the surface of the water, you have a perceived wind speed, direction of your boat, and up on the mast, you have perceived wind speed, well, from the direction of the wind. So obviously, there must be a rotating direction of wind speed. And this with changing velocities. So that's a classical three-dimensional boundary layer. And of course, the description of these boundary layers becomes increasingly difficult because, well, in 3D, things tend to be more difficult. There are some classical cases where this is being studied, and I would quickly like to point out on our next slide the rotating disc. I also have pictures of rotating cone, and I would like to end up this lecture with a picture of a swept wing, just to bring you back to the actual technical application. But maybe first, let's take a look at the rotating disc. This is, again, a situation which should help you to appreciate why a boundary layer is three-dimensional. So what is the situation? You have a disc, like the gray disc here, that is rotating. That's spinning disc, like a gramophone. Huh? And you have some flow coming from the top, impinging onto this rotating disc. So obviously, if we forget about rotation of the disc for a minute, along a radial line going from the center of the rotating of the disc away in radial direction, we will get a boundary layer like that. Huh? This is the boundary layer just due to the impinging airflow. At the same time, if we for a second just forget about the impinging flow and just look at the rotation of the disc, on the surface of the disc itself, we will perceive, if we're sitting on the disc, we perceive an airflow. And actually, not when we're sitting on the disc. If we're looking at the disc, because the fluid has to move, has no slip on the disc, and the disc is moving, the fluid will move in tangential direction with a high speed, with the speed of the spinning disc, and this velocity will decrease as we go away from the disc. So we have two separate effects, one going in azimuthal direction and one going in radial direction. And obviously at the wall, we have zero radial velocity, but a high azimuthal velocity. So we have a resulting vector pointing in azimuthal direction, and far away from the disc, the azimuthal component decays to zero, and the radial component goes to its maximum velocity. So the resulting vector is pointing in a radial direction. So it should be clear now that we clearly have a rotating boundary. These boundary layers are important from a technical point of view because they're much more unstable than, for instance, a Blasius boundary. These boundary layers are much more likely to create turbulent flow than classical two-dimensional boundaries. You see here on this visualization on the left, you see here structures. These are actually unstable structures. Out here, these are turbulent structures where it's like gray, like this foggy structure, where you have more of these spiral structures. This is like the onset of an instability. But we'll look into this in 3 weeks. Similarly, you have a situation of rotating cone. You can think of this as a ballistic object, like a bullet, a spinning bullet flying through the air. Again, on the surface, the velocity will be dominated by the spinning motion of the bullet or of the cone, and far away from the wall, the velocity will be dominated by the oncoming air with respect to the bullet. And you see that just by changing the rotational velocity, we can create turbulent flow in this three-dimensional boundary. So that's the story about three-dimensional boundary layers and why they're relevant. And where do we find them in practice? Well, we find them actually on many, or actually nowadays on all commercial airliners, which have swept wings. Right? I'm sure you have noticed that all commercial airliners have wings which are pointed like a bit like an arrow with a sweep angle of around 30 degrees. Actually, if you look at the history of commercial airliners, like 50 years back up until now, you would notice that the sweep angle has increased over time. This has a lot of benefits. It has something to do with compressible flows, with airspeeds of the airliners getting close to the speed of sound, and there having swept wings is beneficial. That's why it's done in the first place. Having a swept wing actually creates also issues with boundary layers. And we see that just due to this sweeping of the wing, we don't just have a normal flow velocity impinging on the wing, on the blunt edge of the wing, like shown here, down here in the diagram, like this impingement at the leading edge. We also have perpendicular to that, in the span-wise direction, or shown here, span-wise component, a sweeping flow, a flow going in the direction of the sweeping. And this creates relatively complex three-dimensional boundary layers on the leading edge, which are highly turbulent. This actually turned out to be a problem in the 1950s, where they had these X-wing, no, it's not called X-wing, the X aircraft program. NASA or NACA at that point, they started developing these supersonic airplanes, or they wanted to go through go beyond Mach 1, and they realized they need to do sweep angles, high sweep angles for that. And when they used their their airfoils, which were optimized for zero sweep angle, and they just swept it back, they obtained a lot of turbulent flow. So that's when this whole research on 3D boundary layers started. So this is the leading edge boundary layer. You also have it up here on the accelerated side, where we had these Faulkner-Scan boundary layers. Faulkner-Scan boundary layers with a favorable pressure gradient to accelerate the flow. In that case, because we have now a sweep velocity perpendicular to it, it becomes more complex, and Faulkner-Scan boundary layer solution was looked at by a guy called Cook, and he came up with the Faulkner-Scan-Cook family of boundary layers, which are now three-dimensional. So it's yet another extension of boundary layers. And it's also known, well known, that they are rather unstable and create a lot of problems with swept plates. So this was my last slide, just showing you a bit of an idea of where this whole boundary layer theory can go to three-dimensional boundary layers. It's very important. We find them in all kinds of technical applications. With this lecture, we're finishing up this block of viscous flows, right? We had viscous flows 1, we looked at exact solutions. Viscous flows 2, we looked at low Reynolds number. And now viscous flows 3, we looked at higher Reynolds numbers boundary layers. So this completes everything. Next week, we will continue with everything outside the boundary layer, which already hinted today are boundary layer, are flows which are irrotational, where viscosity will not play a role. Different story, but once we have the two things together, boundary layers and outer flow, we can stitch everything together and we can start understanding how airplanes are flying. We can start understanding full aerodynamics of objects. With that, I would like to close. I will stop here and let me just switch off my screen. I will stop here. I will switch off, and I hope that Kai can stay online. We tried that if I switch off, then not everything ends. If it does, please check your email. Kai will send you a link, or I will send you a link via email to join the session again. Otherwise, thanks for watching, and I'll hand over to Kai, and I'll see you again next week. Okay, bye-bye.